Yeah, morning everybody, or afternoon, wherever you are in the world. My name's Mark. I'm obviously the engineering director here at Mastenbrooks. What I would like to do first of all is give you a quick introduction to Mastenbrook as a company. We are a family-owned private business employing about 40 people. All our operations are run from a single UK site. We're currently in our 48th year of trading. And over those 48 years, we've managed to produce upwards of 850 machines, a lot of them sort of unique, bespoke machines. And we have sold into 65 countries around the globe. On a personal note, I've been with the company 46 years, and we operate everything from a small factory in a rural part of the UK. The area is not renowned for engineering, but what it is, it's very like the Dutch sort of heritage of flat, low-lying land that needed drainage. And that's where the company originated from when the sort of the main John Mastenbroek came over from Holland to import machines into the UK and help drain the fens, the area around where we're based. And to start with, he struggled with getting the machines to work. The ground conditions were slightly different. So that went from an importer to actually a manufacturer in a very, very quick space of time. What we have in the UK is a very small sort of capacity. So we manage a limited number of build slots in a year. Our build capacity and design office capacity is split between standard build machines and then the very special bespoke projects. And some of the slides are going to be spoken over by Steve, who's one of the three lead engineers who are assigned to each machine build.
Yeah, hi everyone. So I'm Steve. I have been a design engineer for 18 years, as I mentioned earlier. Been with Mastenbrook for about 10 years, but I've been using Inventor for 13. Used Vault with the previous employer, and been using AutoCAD since university days. So I'm pretty well versed in those Autodesk products. I've also spent 5 years using SolidWorks too, so I've had quite a bit of practice with CAD software. As Mark mentioned, I'm one of three lead engineers here who are assigned to each machine build. And that means we sort of oversee the projects from design until the machines roll out the door. So that's me. I'm going to hand back to Mark to sort of guide you through our product range a bit.
Right. This slide you see basic product range, trenching machinery. The first slide on the left, the center slide is crawler truck, which helps with the backfilling of the trenches, and then we do a range of plows. Our product range is very varied, with a common goal, which is trenching or burying cables or pipes into the ground. Smallest machines are for glass houses, utility, small projects, orchards, golf courses, can weigh around 7,000 kilos, which is about 15,500 pounds. We're trenching depths down to 1.4 metre, 4'6" approximately. Our largest machines come in around the 130,000 kilos, 130 ton mark, sort of 300,000 pounds, with trenching depths down to 18 metres, 60 foot. So products installed include drainage pipes for the removal of excess water on farmland, electricity, gas, water, sewerage, telecoms, fibre optics. They're all for sort of the utilities sector. And then bentonite and cement for the containment of fluids or leachates and wastewater, and then also river embankment stabilization. And then over the last 10 years, we've done an awful lot of work in the burying of subsea cables as well for the offshore wind farm projects. Next slide. This is a recent project which we call a 1717 Bulldog. Mastenbroek are proud to have our machines exported and working well in America. We all know the issues on the West Coast with the frequent deadly fires. You know, they're causing a great deal of grief over there. And this machine, this 1717 Bulldog, was developed from a European style rock trencher. But what its unique abilities is it has the ability to work in confines of the mountains of the West Coast with steep, narrow, winding roads. So it buries a lot of overhead cables, a lot of services to protect from the wildfires, but also helps by reducing the arcing and sparkings that are seen to be the root cause of some of the fires. Can you swap slides? Recent projects, dewatering, deep trenching, large dewatering machines that reduce local groundwater tables to aid during the process of building industrial estates and housing developments, soil stabilisation down to depths of 60 feet, used for water containment on levees and riverbanks to help with the reduction of seasonal surges of water from washing the banks away. Ring fencing landfill sites for the containment of leachate that can then be collected and dealt with, so the environmental impact is managed and reduced. We have lots of challenges with the development of these machines. We produce some are very small, some are very large. On this particular project, the transportation of the machine was critical. So we had to make the machine modular for disassembly. So the whole machine is in transportable loads. We're still maintaining all the strength of a trencher capable of trenching down to 60 feet. You can. Another recent project, we get heavily involved in the Subsea department, which in principle is the burying of offshore cables for wind farms. We're often commissioned to be involved in these projects that require existing designs to be redeveloped. This subsea project started life burying large subsea gas pipelines. We were asked to aid in the transformation to turn that style of machine into one that is more current, as in the burying of electrical cables for wind farm projects all around the UK. What we can bring to these projects is near on 50 years and thousands of man hours of experience that we have in burying these style of products. No matter where that trench needs to be cut, we are capable of coming up with a technology that allows us to effortlessly transform any machine into what we want it to do. And for us, being able to bring that to the table is crucial for the growth of Mastenbroeks.
Okay, so we're going to talk a little bit about common challenges that we have here. Roughly speaking, we sort of split our challenges into design and manufacturing, but of course they're all linked by the software that we use. So first and foremost, it's important to understand that our machines are not road-going vehicles, so they have to be transported between sites. And whether we choose to design our vehicles as a complete machine or whether we do them as modules that can be disassembled and reassembled on site, we're limited in footprint by transport legislation. And that footprint doesn't really change over the years. So our biggest challenge is usually packaging. You know, we tend to pack more into a machine these days, but the machine footprint doesn't get any bigger. So a good example of that you can see on the screen there is one of our engine modules. And you know, as engine emission standards tighten up, we've had to adapt for a more complex exhaust system. Where we used to only fit one can, we can now fit two. There's usually extra pipe work, which all has to be run at controlled angles and lengths. We need to wrap those exhaust pipes to control temperatures. There's a whole array of sensors, and we have to find room for an additional tank for AdBlue. So that all sort of takes up extra space. The knock-on effects of fitting more in is obviously the reduced access for maintenance, and of course increased labour for fabrication and assembly. There's other design challenges too. I'm sure we're no different to a lot of manufacturing sites out there where we have constantly updating safety standards, and we need to incorporate new technology when it comes along. So a couple of examples, recently we've had to incorporate new information screens in the cabs, which record things like engine data, or we've started to incorporate AI camera systems with human form recognition to improve the safety around the machines while they're working. From a manufacturing point of view, we face similar challenges to everybody else. We're trying to be efficient in all our processes, whether that's managing files and legacy designs, whether we're trying to ensure an accurate bill of materials, for example, always striving for a high build quality, lowering our costs and managing the build time. Next slide, please. Thank you. So how do we solve them? We solve them, those challenges, in a number of different ways. As a design engineer, the more information I have at my disposal, the better decisions I can make. So we make our models as comprehensive as possible. That's going to help me understand the usable space early on. It's going to prompt earlier communication with hydraulics guys, electrical guys, or service departments. It prompts detailed discussion with suppliers and customers too. And we save models for every machine we build. So this helps us to retain the lessons that we learnt on those builds, and it records the nuances of each of those builds too. So those models become a good reference for those that are unfamiliar with the machine, or for new and future employees who don't have the experience. So our CAD models have become the primary source of information for our builds, and it's the first place we check if there's a manufacturing issue. Now, to be efficient as possible with our design work, we always install the latest version of Inventor, primarily because if there's a new feature that improves our productivity, we want to be using that straight away. We have a huge library of 2D AutoCAD and paper drawings, and we find it's best to translate those into Inventor whenever it's needed, because then we get the additional functionality of being able to check clashes, make quicker changes, output parts lists, all the things that you couldn't use to do with the 2D CAD. And translating the design also sort of in small ways helps to future-proof our IP a little bit. And just basically touching on efficiency again, if we do import CAD models from suppliers wherever possible, so engines, pumps, that sort of thing, just saves redoing it all. But the CAD data, it's no use unless we can communicate it to others, right? So whether that's subcontractors, in-house technicians, customers, and some of the ways that we do that, one of them is developing a range of standard operating procedures that heavily use the CAD data. So a couple of examples on your screen there. We record things like the order of build of an assembly, or we list information like the torque values for fasteners, all the sort of useful information that technicians might need. And that involves making good use of the view representations, position representations, and model states. But ultimately, we find that 2D drawings are still an effective way to pass information to suppliers and technicians. There's a legacy of the guys using those sort of drawings, and it just helps. But we do send 3D images down to our workshops quite regularly to explain things in a bit more detail. And sometimes they come to the office to have a look at the model on the screen where we can rotate it or section it, that sort of thing. And to help with our processes, we do utilize the model. Our iProperties, for example, we load up with part numbers and descriptions, that sort of thing, and of course parts lists to get the assembly quantities to ensure our bill of materials are accurate. And that's obviously fundamental to ensuring that everything goes smoothly once it leaves the design office. And we're able to translate our CAD model parts lists into spreadsheets where they can be edited or imported into our ERP software, but we can filter that spreadsheet, track the parts and sort it by process or status. And finally, we have a dedicated design engineer who creates exploded views for parts books, which are supplied with each and every machine. And this helps with after sales care and maintenance engineers as well. Next slide, please. Thank you. So we do a little FEA here. We find that FEA tends to be useful for us on bespoke designs rather than on the standard machines. Mastenbroek has a reputation for longevity and robustness in our designs, so analysis can help to ensure that we continue that trend. We tend to use it for analysing areas of concern or proving concepts to customers. What we don't do is we don't manufacture in any great quantity. We're not making thousands of machines every year. So that doesn't really help us with FEA. We don't use it to save a little bit of material on thousands of parts to save cost or anything like that. And we don't need FEA to help us reduce weight either. Weight can actually be useful on the trenchers. So we tend to use Inventor's own stress analysis for most of our results, but on a couple of more recent bespoke machines, we have used Nastran for a more detailed analysis. As I mentioned earlier, the CAD data's no good unless we can communicate, and we feel it's important to use that CAD data and the software to its maximum potential, not just in manufacture, but in sales and marketing too. You've got to ask yourselves a few questions like, how do we prove to the customer that we meet their specification? You know, we need to clarify transport sizes to help them manage their logistics. We need to show how their chosen options fit on the machine. We need to show the range of articulation of linkages and tooling so they can consider any operational restrictions. And how do we reassure our customers that our bespoke designs are functional and robust and value for money? How do we provide the right level of communication for the right type of customer? You know, some of our customers are long-standing customers with a deep level of understanding of the machines and their operation. Some are experienced technical managers, but perhaps not familiar with Mastenbroek designs. Some are new to the industry and need far more support and information. So how do we get swift approval for our designs so that we can meet our designated build slots? And there are a lot of tools in Inventor that we can make use of. More recently, we started to make good use of the shared views, which I know Jim touched on earlier. We find them to be very quick to use, easy to use. Our customers find them very easy to use too. And they're best for customers with greater technical understanding, the guys who you're happy for them to pull the model apart and really go into detail on. But we also use video capture of driving constraints just to show the articulation of links, and we use 2D drawings as ever. So sometimes we might share our screens on Teams meetings to help walk a customer around their machines, and we export screen grabs all the time. So there's plenty of good options to get the information across in a useful way. Next slide, please. Thank you. So a lot of our marketing has sort of explained that we have very large CAD models. So this is a little bit about how we work with large assemblies. I sort of touched on why we have such large assemblies. There's a lot more benefits. So of course, having an accurate mass, for example, in our assemblies helps with engineering calculations or with planning for safe handling. It ensures we have sufficient detail for accurate manufacture as well, which improves the end quality of the machines, of course. Now, to sort of avoid any slow performance or crashes, I think how we structure our models helps a lot, and we generally try to follow best practice where we can. We have a decent spec of desktop PCs generally for each user. But what helps most, I think, is making good use of sub-assemblies at the top level. So the image you see in front of you there, the entire undercarriage is one sub-assembly. The entire main frame, which includes the engine and hydraulics, is one assembly. So we have much fewer constraints at top level. And that also allows multiple designers to work on the same project at the same time too. Now, for our CAD data in general, we have a reasonably flat folder structure, which groups files mainly by machine type or into common libraries such as hydraulic components. At a part level, we tend to remove adaptivity once designs are finalized. We reconstrain to ensure the models are stable and reduce the processing in the background. We make good use of model states too for suppressing options such as different lengths of digging booms or pipe boxes that come with one machine. And we generally try to quickly resolve constraint issues and interferences, which just helps Inventor to process the views a bit easier. So cutting metal, we don't have a massive amount of time for any single project. We go from a blank screen to cutting metal in a matter of days, and the machine is rolling out of the door in 12 to 16 weeks. In ideal circumstances, we would wait until the design is complete before releasing drawings from the design office. With thousands of parts to process, we release as much as possible, as quickly as possible. So we break the machine bombs down into phases and start with phase one, which is always the undercarriage because we physically build the machine from the ground up. And our models tend to try and reflect that build process. So the phases help us by allowing us to release the phases that we don't need to do any design on. And it buys us time for the working on the design of the phases that do need it. And it helps us prioritize our design work too. We have a good reputation with our suppliers for high quality drawings because we believe that the level of detail in the models and the information on our drawings must be high to reduce the risk of manufacturing mistakes that arise from making assumptions. We have a small design team that means it's easy to be consistent in our approach and to share our learning. And we can be flexible for changing our drawing standards if an improvement's identified. We have an ever-growing library of sketch symbols to record information that can be inserted into the relevant drawings. So generally there are notes relating to particular materials or processes. We tend to use local suppliers, which means we can quickly visit them to help with problem solving, keeping track of lead times or quality. And we can build good relationships so that we can understand each other's needs. And when it comes to sharing files for manufacture, we create and issue new files with every order, which helps prevent a mix-up with revisions. But that's very time consuming. And so Jim again mentioned earlier the use of iLogic. We have made pretty good use of iLogic rules to generate those files as quickly as possible. And for those that haven't used iLogic before, I'd recommend it. There's plenty of help on the forums. We don't generally use the forms, but we do have the rules to create DXFs, PDFs, that sort of thing. But we're not just a design house. We are fortunate to have a well-equipped machine shop. So that helps speed the process up because we can get drawings to the machine centers quickly, and ultimately we're in control of the lead times. So I'm going to pass back to Mark to explain our relationship with Autodesk a little more.
Yeah, basically, I'll give you a little bit of history into the design office. I joined the company in 1979, where we were using drawing boards and ink, and I first stepped into AutoCAD in 1986. Very good tool, used it all day, every day, very good for what we wanted to do, but it had its limits when it came to big designs, big engineering projects and that. So I first stepped into the 3D Inventor at release 4.3. Found it amazing what we could do with it, what we could turn out. We realized it was no longer just a drawing tool, it was a very good sort of sales tool. And we were quickly sort of outgrowing what we could do within the Inventor. And we decided to join. We were invited into the beta test program in 2013. And we felt at the time that we could help, we could give the ability to give really good feedback on what we were achieving, how we were getting the results, and what we were doing and how we were doing it. Because, you know, there wasn't many rule books back then. A lot of people was sort of unsure how to get high-end, large-scale models. So it was very good to share our knowledge with the Autodesk developers. And our aim was always to push the limits of the software in the areas that would actually benefit us the most. You know, that core product. We need to get drawings out quick, but we need to be able to manage that information. And large, fully working assemblies that were useful to our day-to-day designers. You know, we don't actually test beta software. We use it all day, every day. We decide on a date, we jump onto the beta version and we carry on. We feel it's the only true, real test for the next release. You know, we work in that beta software 50 to 60 hours a day. And what that allows us to do is to really push that software and what we can do with it. So in the 50 or 60 hours a day, you know, that's 170 hours a week, we're reporting back to Autodesk what we can find. From the very early days of the program, I took it upon myself to actually share data sets to allow Autodesk to use our large assembly models to push and aid the development of the software to create a better product. And in turn, from that, we get access to the development team, the marketing images we use for all our social media platforms, and we've got a very good two-way relationship in the way we use the beta program. Next slide, please, Jim. Look what's possible. At Mastenbrook's, we more often than not take for granted what we do. And it's not until we pass our models over to Autodesk that actually we can see what it can create. It can create an awfully good sales tool, which allows us to, I think Steve mentioned it earlier, you know, we used to sell machines to people that owned companies and drivers, and you would lay a flat 2D blueprint out on a table and everybody understood what they were looking at. Those days have gone now. You know, you're sort of talking to government departments, you're talking to boards that have been set up for drainage, and they're not very capable of understanding flat drawings. When you bring in that third dimension, what that allows them to do is to see that depth and get a feel for a machine and what it looks like. And it's become a very, very powerful sales tool to showcase what we can do. And we use it to design and the development of new conceptual ideas. Not only do we design the conceptual stuff, what it allows us to do is to put that in front of the customer and say, look, you know, this email or these few words on a sort of a review, this is what this is going to turn out. You know, this is what it's going to look like. This is what it's going to work like. And we can actually show a sort of a driver, look, this cab position, this is where it works well. we know you want to sit here, but it doesn't lend itself to be able to drive this conceptual machine in the right way. And I think Steve's touched on it as well. We very quickly use all the information for the instruction manuals, the maintenance manuals, the workshop manuals, marketing and social media. And we've used it for a great number of years now, and we're always pushing the limits of what can be done. But occasionally, you just have to sort of tip you out to the engineers at Autodesk and say, "Wow!" with some of the images that turn out, like this one. And if you could just click on again, it's no longer just about flat pattern drawings. It's amazing what can be achieved and what's coming next. Who knows? But it's very good. It's very powerful, and we use it to its best abilities. Next one, Jim. Yeah, just what I would like to say is we as a company, we're proud to be in a partnership with Autodesk. We're proud of the amount of effort and worth both sides come in. I'm very proud of the small and dedicated design team that we've assembled down here at Mastenbrooks. And lastly, finally, thank you all for listening to both Steve and myself.
Yes, thank you.